Welcome back to this explainer. So as we wrap up the wave-particle duality chapter of our quantum series, we are faced with a pretty massive challenge. How do we actually translate the wildly abstract math of quantum mechanics into the dynamic physical journey of a wave packet? I mean, let's be real. Whenever we talk about the quantum world, it can so easily feel like we're just staring at a chalkboard full of impenetrable equations, right? But today, we're going to visually track how quantum probability actually moves, how it breathes, and how it interacts with our physical reality.
Okay, let's dive right into the central paradox here. Think about it. If a basic quantum wave literally goes on forever, stretching out to infinity, how on earth do we ever use it to represent a localized particle? Like, an actual electron sitting right there in a lab. To figure out how to find a particle in space, we first have to wrap our heads around how quantum probability actually moves and flows, instead of just assuming it exists everywhere all at once.
So, here's our quick roadmap for today's explainer. We're going to cover what exactly a wave packet is, how it moves and spreads over time, the actual flow of quantum probability, what happens during collisions and tunneling, those weird interference effects, and finally, how we go from pure math to actual measurement.
All right, let's kick things off with Chapter 1. What is a wave packet? This is absolutely the foundational concept of quantum localization.
Okay, picture a single pure sine wave. It extends out infinitely, right? And because it's everywhere at once, it tells us absolutely nothing about where a particle actually is. But what if we superimpose multiple waves? If we blend waves with slightly different wavelengths, kind of like mixing different musical notes to create one single sharp, distinct beat, they actually interfere with each other. They cancel each other out in some places and build up in others. And boom, that creates a localized packet. This finite little region of space is basically the physical bridge between a mathematically infinite wave and a measurable physical particle.
Which brings us to Chapter 2, moving and spreading over time.
Now, when this localized packet moves, we really have to distinguish between two completely different speeds, or velocities. First, you've got the phase velocity. That's the speed of the individual internal ripples inside the packet. And second, there's the group velocity, which is the speed of the entire wave packet envelope as a whole. A great way to visualize this is to think of it like a flock of birds. The individual birds darting around inside, that's your phase velocity. But the speed of the entire flock moving south for the winter, that overall movement, is your group velocity.
And you can see this dynamic playing out beautifully here. Notice how the group velocity is what actually carries the bulk of the probability forward, while the phase velocity is just representing those rapid internal oscillations. This is crucial because in quantum mechanics, it's the group velocity that actually aligns with the classical speed of the particle we're trying to track. The phase velocity on its own simply cannot represent the motion of the entire wave packet.
But as this packet travels, something really fascinating, and honestly a bit counterintuitive happens. Dispersion. Because the different frequencies trapped within our packet actually travel at different phase velocities, they inevitably start to drift apart. The math behind this dispersion relation tells us that over time, our tight, neat little wave packet can't hold its shape forever. It naturally broadens. Its width physically increases, meaning the probability of finding the particle gets smeared out over a larger and larger area of space as the clock ticks on.
Okay, moving on to Chapter 3. The flow of quantum probability and how we actually track this movement. Instead of drowning in impenetrable math here, let's use a fluid analogy that comes directly from the quantum continuity equation. Think of probability as a sort of inhomogeneous fluid. In this analogy, the probability density is like the volume of water sitting in a specific area, and the probability current is the measurable rate of that fluid flowing around. And just like water, probability is locally conserved. If the chance of finding a particle in one spot goes down, well, that probability fluid had to flow into an adjacent area. It doesn't just magically vanish into thin air, it flows.
Now for Chapter 4, collisions, reflection, and tunneling. Let's see what happens when our fluid-like packet slams into an obstacle.
When you track the spatial probability density before, during, and after a collision with a barrier, the dynamics are just wild. You start by watching the packet approach, nice and smooth. But during the collision, it explodes into these jagged, incredibly complex peaks. And then, finally, a tiny, distinct peak somehow makes it past that solid barrier. Even when the classical energy of the packet is way too low to actually cross over, the wave function physically pushes its way into the forbidden region. This specific behavior right here is exactly why quantum packets matter so much. It's literally the underlying mechanism that makes modern semiconductors and the device you're watching this on possible.
You see, a quantum collision isn't just a simple bounce like a tennis ball hitting a wall.
It happens in 3 distinct phases. First, the envelope approaches the barrier. Second, and this is key, it actually dwells in front of the barrier, engaging in highly complex self-interference, and finally, it physically splits. The vast majority of the probability fluid reflects backwards, sure, but a tiny, crucial fraction transmits or tunnels right through to the other side.
This leads perfectly into Chapter 5, Interference and Superposition Effects. This is where the real quantum magic happens. This middle step is a deeply counterintuitive concept. As the wave packet hits the wall, its front end reflects backwards and crashes directly into its own back end, which is still moving forward. The particle literally spends time held up in a standing wave, interfering with its own reflection before the tunneling event even finishes. This generalized dwell time in front of the barrier heavily distorts the shape of the wave packet, completely destroying any clean, neat definition of an incident peak while the collision is happening.
And finally, Chapter 6, From Math to Measurement. How do we interpret this in the real world?
When physicists actually sit down and measure the time it takes for a tunneling particle to pop out on the other side of a barrier, it is so tempting to just think of it like a classical transit time. You know, like tracking a car driving into a literal mountain tunnel and waiting for it to exit so you can clock its speed. But here's the catch. The transmitted pulse is not the exact same entity as the incident pulse. Remember, over 99% of the packet's energy got reflected back. The tiny sliver that actually makes it through has been heavily filtered and totally reshaped by intense self-interference. So the input peak and the output peak, they aren't simply the same object seamlessly moving from point A to point B.
Which leaves us with a profound mystery about the dynamic flow of reality. Think about the journey we just took. We set out to localize a particle by building a wave packet. We watched it flow like a fluid, we saw it spread out, crash into a wall, literally interfere with its own past reflection, and finally emerge completely transformed. So if the peak we measure exiting the barrier isn't exactly the same peak that entered, what is it that we are truly tracking in the quantum world? I'll let you ponder that one. Thank you so much for joining me on this explainer, and keep questioning the nature of reality.